Bangladesh has achieved 100% national electrification. Now, the power sector is targeting a new metric, generating 30% of total energy from renewable sources by 2040. To hit that target, the standard playbook relies on utility-scale solar parks, but these require massive, contiguous physical footprints. This visualization maps out the specific mathematical bottleneck. Generating a single megawatt of solar power requires approximately 3 acres of physical land. Scaling that footprint up to match the gigawatts required for the 2040 target would overrun massive tracts of the country. The local geography provides no such surplus. In a nation this densely populated, the absolute scarcity of available land makes traditional utility-scale expansion physically impossible. Because available land is prioritized for food security and urbanization, hitting the 2040 renewable targets requires a transition away from the centralized solar park model. The government engineered a regulatory solution to bypass this physical land constraint, the Net Metering Guidelines 2025. The core mechanism of net metering targets heavy industrial power consumers and transforms them into active energy exporters. Instead of acquiring new real estate, the grid leverages their existing, unutilized factory rooftops. Crucially, these new local generation nodes do not rely on expensive physical battery storage. Any surplus power they generate is injected directly back into the national AC grid. A bidirectional accounting mechanism governs this exchange. Surplus exported electricity is logged as credit units, which are then settled against the facility's future utility billing cycles at mandated tariff rates. Overlaying solar infrastructure onto existing industry bypasses the physical land crisis. However, this transition to decentralized generation creates a complex financial and electrical engineering challenge. The immediate bottleneck for industrial solar adoption is economic. Outfitting a massive factory rooftop requires a prohibitive upfront capital expenditure, or CapEx. To eliminate this upfront capital barrier, the 2025 guidelines formalize an operating expenditure, or OpEx framework. This flow diagram illustrates the resulting tripartite agreement connecting the consumer, the distribution utility, and a third-party OpEx investor. Here is the flow of capital. The third-party OpEx investor funds and deploys the solar hardware on the consumer's roof, meaning zero initial cost to the facility owner. Next is the flow of energy. The hardware generates DC power, which is consumed locally by the factory, with the remaining surplus pushed outward into the distribution utility grid. Finally, the flow of compensation. Credit units accumulate from the utility to the consumer for the surplus. The consumer then routes a fixed discounted payment stream back to the OpEx investor to cover the hardware. Standardizing this tripartite agreement within the national grid guidelines reduces legal friction. It de-risks the environment to pull institutional investors into the decentralized network. The OpEx framework financializes the decentralized grid by decoupling capital expenditure from roof ownership. But deploying it safely across the country introduces severe physics problems. Decentralization comes with an inherent danger. Injecting thousands of intermittent inverted DC to AC power sources into a traditional 33 kilovolt distribution network can cause catastrophic grid instability. This engineering schematic highlights the interconnection point. This is the highly regulated boundary where the consumer's local generation meets the national utility grid. The first critical engineering requirement at this boundary is mitigating voltage fluctuation and harmonic distortion. Inverters must output pure sine waves. Failure to do so injects dirty power into the line, degrading power quality and potentially damaging sensitive manufacturing equipment on neighboring industrial circuits. The second major requirement is reactive power compensation and the maintenance of the power factor. A strict power factor must be maintained at the interconnection point to prevent transmission losses and localized voltage drops across the network. But the single most critical safety protocol mandated by the grid guidelines is anti-islanding protection. This addresses the specific hazard of backfeeding. If the central utility grid fails or is deliberately shut down for maintenance, local solar nodes cannot continue pumping power into the dead lines. If an inverter creates a localized island of power, it risks injecting lethal voltage into external utility lines that repair crews assume are de-energized. The local inverter functions as the safeguard. It continuously monitors gray frequency and physically severs the interconnection point within milliseconds of a detected failure. The viability of the entire national net metering policy relies entirely on these rigorous inverter-level grid codes, protecting the macro network from micro-level instability. This map illustrates the baseline: over 3,700 active installations, generating 185 megawatts. As those nodes multiply across the industrial map, capacity ticks upward exponentially toward the 2040 targets. This massive new power plant is being constructed entirely invisibly, requiring zero new land acquisition. The 3-acre per megawatt physical bottleneck has been permanently bypassed by leveraging existing industrial architecture. This framework transforms static commercial roofs from depreciating assets into active, revenue-generating, grid-supporting power plants. This scale of distributed generation is only technically possible because of the uncompromising OpEx financial structures and strict AC synchronization protocols governing every node. For land-constrained markets, securing the energy future depends on the synchronized deployment of decentralized power.